Hi all, I'm Hannah Pasandi. In this talk, I will cover direct-to-device D2D satellite communication and discuss their current advances, challenges, and future potential. This is a joint work between UC Berkeley and Inria, Lyon. To begin with, let me start with a scenario. Imagine an injured hiker stranded in the wilderness, or a fisherman navigating the Arctic waters in 2022. For them, communication wasn't just a convenience, it was their lifeline. However, traditional networks often fail in remote areas, leaving millions disconnected during critical moments. This is where direct-to-device satellite communication steps in, enabling unmodified devices such as smartphones or IoT sensors to connect directly to satellites. The impact? Over 5 and 20 plus million people who lack mobile broadband access could finally be connected. Now, let's take a closer look at D2D Satellite Communication Foundation. At the core of D2D are three foundational technologies: LEO satellites. These satellites orbit closer to Earth, reducing latency and providing stronger signals compared to traditional high-orbit satellites. For technology, imagine moving from shouting across a room to whispering directly into someone's ear. Beamforming focuses satellite signals precisely where they're needed, minimizing interference. In terms of dynamic spectrum sharing, this allows satellite operators to integrate seamlessly with mobile networks, harmonizing spectrum allocation for efficient communication. Let's talk about the three generations of D2D communication. The evolution of D2D communication is fascinating because if you look at it, it was there from years ago. In Generation 1, devices needed external antennas, offering speeds of 2.4, 9.6 kbps for messaging and basic voice services. Examples include Iridium and Globalstar handsets. In Generation 2, internal chipsets allowed for SMS and voice calls, with wide beam antennas tolerating mobility. In Generation 3, the latest advancements enable unmodified smartphones to achieve speeds of 18 Mbps downlink DL and 7 Mbps uplink UL per beam, making real-time multimedia services a reality. Now let's delve into current D2D satellite communication models. D2D communication supports various models: DTS IoT, which targets IoT devices supporting uplink speeds of 1 to 3 kbps, LoRa, LR, FHSS, and downlink speeds up to 1 Mbps, DTC, or direct-to-cell, designed for feature phones and IoT devices, offering kilobits per second uplink and tens of Mbps downlink for advanced satellites, DTS, or direct-to-smartphone, that focuses on smartphones with enhanced hardware, achieving Mbps speeds for both uplink and downlink. To take a closer look at DTS IoT model, here's how DTS IoT works. Uplink speed, 413 kbps for LoRa and LR FHSS. Downlink speed, 50 kbps 1 Mbps for standard systems. Advanced systems may exceed this. Device density, over 10,000 IoT devices per satellite footprint can operate simultaneously. Data is relayed to the cloud via high-speed terrestrial links of 110 Gbps. Now, let's look at some of the industry status. What was once science fiction is now a commercial reality, starting by Starlink from SpaceX. With over 4,000 satellites, Starlink offers global broadband coverage with plans to support mobile device connectivity. Another example is AST Space Mobile, developing a space-based cellular broadband network for standard smartphones with 248 LEO satellites planned. Globalstar and Apple. Recently, Apple have invested $1.5 billion on Globestar, Apple's satellite-based SOS feature, and the new upcoming road assistants demonstrate the real-world practicality of D2D. Here, we would like to highlight the transformative works in D2D. Let's now highlight three significant contributions that have advanced D2D communication: Mosaic, multi-tenant satellite access. introduces a pay-as-you-go model for satellite sharing across operators, reduces service latency by 4.7x to 14.2x, Space Core, or stateless mobile core, decouples network states from satellites using geospatial addressing, reduces signaling overhead by 17.5x, finally, or spectrum-efficient IoT satellites, leverages Doppler shifts for packet detection under low SNR conditions, achieves 3x better packet detection rates and 80% decoding accuracy in real-world deployments. Now looking at the challenges ahead and future directions. Despite its promise, D2D communication faces significant hurdles. First, technical challenges, signal attenuation, Doppler shifts, and maintaining link stability in high mobility scenarios. Second, economic barriers. The cost of deploying and maintaining satellite constellations remains high. Third, regulatory complexities. Coordinating global spectrum usage is a political and technical challenge. Now considering the future of D2D, where do we go from here? Following are the directions we expect that D2D will go through. 1. Hybrid satellite terrestrial networks, combining satellite constellations with ground networks for seamless connectivity. 2. AI-driven optimization. Predictive algorithms could dynamically route signals, avoiding bad weather or congestion. 3. Scalable business models. Pay-as-you-go services make connectivity affordable for underserved communities. Finally, to conclude, let's return to our fisherman navigating the Arctic. His connection isn't just about convenience, it's about survival, innovation, and opportunity. As a final thought, D2D communication represents a transformative leap toward a world where no one is unreachable, where opportunities know no boundaries, and where the digital divide becomes a relic of the past. Thank you. Let's make this vision a reality.